Hi, I'm Kirty Vedula, and I'm a final year PhD candidate from Department of ECE, Worcester Polytechnic Institute, Worcester, Massachusetts. Today, I'm going to present our ICASSP paper titled Joint Coding and Modulation in the Ultra-Short Block Length Regime for Additive Wide Gaussian Noise, as well as for Bernoulli-Gaussian impulsive noise channels using autoencoders. This is a joint work by myself, Professor Randy Paffenroth, and Professor Donald Richard Brown. Now let's look at an end-to-end communication system pipeline. Let's start with the message queue. Q goes through a one-hot encoder and we get S. S is a set of one-hot encoded messages. S goes through the transmitter, which has encoder and modulator lumped together, and we get SE, a set of encoded symbols. Now these symbols go through the channel and they go through an energy or a power constraint and an impairment such as additive wide Gaussian noise or Bernoulli-Gaussian impulsive noise, and we get a noisy version of SE which is called Y. Now Y goes through a receiver which has a demodulator and a decoder lumped together, and we get P. Now this P goes through a one-hot encoder and we get the final estimate of the message Q hat. The aim is to make Q hat as close to Q as possible. Now let's look at a machine learning alternative for the same end-to-end communication system pipeline. From this picture, we can notice that only the transmitter and the receiver parts have changed and nothing else has changed. So the transmitter is replaced by two layers of neural network, one with fully connected plus ReLU and another with fully connected plus linear. And over the receiver side, we have a fully connected plus ReLU and fully connected plus softmax. And other than that, nothing has changed. And small m stands for the number of real valued symbols transmitted through the channel. And capital M stands for 2 to the power k distinct messages for a block of k bits. Let's take a training example now. Let's consider capital M equal to 16, small m equal to 7. And in order to train, we train them over 100 epochs with Adam optimizer, learning rate of 10 to the minus 3, batch size of 256, and a training SNR of 3 dB. The training SNR should be in such a way that we do not have too many noisy symbols and we do not have too many noise-free symbols. If we see the training accuracy and the validation accuracy converge around 0.97, if we take 1 minus accuracy, which will give us about 0.03, that will give us a block error rate. Now let's look at an example with capital M equal to 16, small m equal to 7, k equal to 4. Even though these values can be arbitrary and autoencoder would work with any arbitrary values, we choose these because we want to compare them to a 7/4 Hamming code with BPSK. Traditionally, there are two kinds of decoding techniques, hard decision decoding and soft decision decoding. We want to compare against these. For comparison, we have our x-axis, which is EP over N0, which represents the SNR varying from 0 to 10 dB. And we have a block error rate as a y-axis here. And here, the blue line represents the hard decision decoding curve, and the black line, which is behind the red line, represents the soft decision decoding curve. The red line in the diamonds represents the autoencoder curve. If you notice, the autoencoder curve overlaps the soft decision decoding curve, and the performance is similar to that of the soft decision decoding curve. So that is the key takeaway from this point. That means the autoencoder learned curve with the same block error rate performance as Hamming 7/4 with BPSK modulation and soft decision decoding, or it can also be called as a maximum likelihood decoding. Now let's look at the code words for BPSK plus Hamming 7/4 and for autoencoder 7/4. If you look at BPSK plus Hamming, it consists of -1s and 1s because these are modulated code words which are modulated by a binary phase shift keying modulation, whereas the autoencoder code words are all random. They lie in between -1 to 1, however, they take random values. And if we retrain the autoencoder, we'll end up in a different set of values. But the important thing to note here is the statistics. That means the properties such as mean, minimum distance, and maximum distance are similar to that of BPSK plus Hamming 7/4. Now let's look at the pairwise Euclidean distance statistics for the code words we just saw. And these are the distances with soft decision decoder for Hamming 7/4 plus BPSK. And this is the autoencoder. If we notice, Hamming 7/4 and BPSK has 3 distinct possibilities. This means they're all lying within a structure that have 3 possible distances from each other. Whereas autoencoder is much more like a gamut, and it has all the sets of distances that are possible from from this point to this point. Now let's look at the conditional block error rate for all the 16 code words. Starting from 0 till 15, we send each code word through the autoencoder and through the Hamming encoder and decoder 70 million times. After sending through them, they make a certain number of errors. Those many number of errors are represented by the dots here. The blue dots represent the errors made by the autoencoder, and the red dots represent the errors made by the Hamming encoder and decoder. If we see the sorted words here, the left one is unsorted, the right one is sorted. If you see the right one here, we see that the Hamming is flattening out and closer to the average Hamming blur, whereas autoencoder does not. This means that all the Hamming code words are equiprobable in making errors, whereas in autoencoder, certain code words make more errors than some other code words. Now let's look at a higher dimensional example with capital M equal to 2 to the 11, small m equal to 15, k equal to 11. Again, these can be arbitrary. However, we pick these values because we want to compare them against a 1511 Hamming code with the BPSK modulation. Now, the axes remain the same as previous plot, EB over N0 on the x-axis, block error rate on the y-axis. Now, if you note, the blue line represents the hard decision decoding curve, and the black line here represents the soft decision decoding curve. Now, if we notice, the red line with the red diamonds is the autoencoder curve, and it beats the soft decision decoding curve by about 0.5 dB. Now, why does this happen? Does it have to do with the structure of the autoencoder, or does it have to do with any symmetrical properties that are present in the Hamming code and that are not present in the autoencoder code, or the degrees of freedom? Let's explore this further. Now let's look at the pairwise Euclidean distance statistics for m equal to 2 to the 11. We picked this because the autoencoder matches with Hamming 1511 plus BPSK, which is shown in the top graph. We see that it has 11 possible distances, whereas the autoencoder has a whole set of possible distances that resemble a Gaussian curve. However, the statistics such as mean, minimum, and maximum are similar to those of Hamming 1511 plus BPSK. Now let's look at the conditional blur for 2048 code words for the 1511 setup. Now, each code word starting from 0 till 2047 is sent through the autoencoder and the Hamming encoder decoder setup 5 million times. Now, this results in an average error made by each code word, and this is represented by the blue dots here. The flat line represents the overall error rate made by all the code words put together. Similarly, the red dots represent the errors made by the Hamming code words, and the flat red line represents the average H-blur, Hamming blur. We are interested in a particular case, although it is obvious that autoencoder clearly outperforms the Hamming case. That means even the worst autoencoder here, the one that makes the most errors, is far better than the one that makes the best errors in the Hamming case. However, we are interested in this corner case. This is code word number 849. We want to analyze the confusion matrix of this code word, which is over here, which is situated over here on the sorted curve. And having analyzed this confusion matrix might give us some more insights. Now we look at the first 15 elements of row number 849 of the confusion matrix. First row with BPSK plus Hamming 1511, second row with autoencoder. We see that in the first row, all the elements in the confusion matrix are in a similar range. Remember, this is in the descending order. So 588 is the highest and 543, and it keeps decreasing. However, they're all in their 500s. Whereas in autoencoder, we start at 788 and go on to 380, and later on we reach to 0 as well. This means that every Hamming code word has equal probability of making an error, whereas in autoencoder, certain code words have more probability of making an error than other code words. This is also reflected by their structure. Hamming code has a symmetrical structure. It has a pattern, whereas autoencoders do not have a pattern. Now, if we take the cumulative sum of these rows, we see that autoencoder has higher cumulative sum for the top 10 distances, and then later on soft decision decoding takes it over. And since this has a linear slope and autoencoder does not have a linear slope, we could say that autoencoder is getting an edge because of these particular code words and because of its asymmetry. Now this concludes the AWGN section. Now let's move on to Bernoulli-Gaussian impulsive noise channels. Now this is the setting for Bernoulli-Gaussian impulsive noise channel. We have our input, and our input enters the bad channel with a probability PB. And if it does, it gets added by a Gaussian noise with a high variance. And it can enter a good channel with a probability 1 minus PB. And if it does, it gets added with a Gaussian noise of low variance. Now the output that we get is dependent on the Bernoulli distribution here, whichever probability we are picking, and the Gaussian noise here. And that's why it's called as a Bernoulli-Gaussian impulsive noise channel. This is a particularly hard case for traditional methods such as hard decision and soft decision decoding. That's why we resort to methods like blanking and clipping. Now we see a couple of traditional methods that are used to mitigate impulsive noise in a signal that is corrupted. Here's a sine wave that is corrupted with an impulsive noise. It has 10 periods. It goes up to 50. And the red dashed lines represent the clipping and blanking threshold. They are said to be the same to maintain uniformity. Here in blanking, we can see whenever we cross a threshold, such as over here, that value is set to 0. And whatever is remaining within the threshold will remain the same. In clipping, however, in the same situation where the blanking sets it to 0, clipping sets it to a particular threshold. That threshold is the same as mean of absolute of signal in this case, and we set it to this value. And these are typically heuristic methods, and these are not guaranteed to be optimal, but they are heavily used in applications such as power line communications, where there is a lot of impulsive noise prevalent in the signal. Now let's consider a training example for a BGIN case, where we consider a Hamming 7/4 example with capital M equal to 16. There are 16 distinct messages, and small m equal to 7 symbols. Now we need to construct a family of autoencoders here for each bad probability, each PB, where PB equal to 0, where we always have the good channel, and so on up to PB equal to 1, where we always have the bad channel. Now this results in a set of autoencoders, 11 autoencoder set here. Now each one is trained for 50 epochs with Adam optimizer and learning rate 10 to the minus 3 and a batch size of 256. And here is a training and validation accuracy for PB equal to 0.1. That means there's a 10% chance of getting a bad channel and a 90% chance of getting a good channel. And we see that we reach about 90% accuracy with the autoencoder. Now let's see some results for BGIN channel with a good channel SNR of 3 dB and a bad channel SNR of minus 7 dB. And the rest of the parameters are similar to 7/4 Hamming code plus BPSK. Notice that the axes have changed. Now the x-axis is PB, the probability of high variance noise or probability of entering a bad channel. So when PB is 0, we always enter a good channel, and when PB is 1, we always enter a bad channel. That's what these horizontal lines represent, when we always enter a good AWGN channel and we always enter a bad AWGN channel. And we also note that the blue line here represents a hard decision decoding, and the black line here over here, the black solid line represents the soft decision decoding. We also have some heuristic methods represented in stars and squares, which represent clipping and blanking. And the red line for the autoencoder, if you see, this conveniently beats all the existing classical methods and the heuristic methods conveniently at all probabilities, starting from 0 to 1. Now, this means that autoencoder is more robust to shifts between a good channel and bad channel, whereas the classical methods and the heuristic methods are not. Now we have a high dimensional case with a 1511 Hamming code. Here we see that the autoencoder beats all the methods, even though not with as much difference as in 7/4 Hamming code, but it still manages to outperform all the heuristic and classical methods. To conclude things, we've seen that learning of an end-to-end communication system is possible with autoencoders for AWGN and BGIN channels. However, we are restricted on scalability because of one-hot encoding. We've also seen that it is possible to gather new insights on well-studied coding and modulation schemes as well. And a couple of next steps to consider in the future are considering BGIN channels with memory, such as Markov-Middleton and Markov-Gaussian models, and applying domain randomization techniques for BGIN channels instead of using a family of autoencoders. Thank you so much for listening to this presentation. I hope you have a great day.